Hi everyone. So in the previous lecture we studied about common source amplifier. We saw different configuration: simple common source amplifier, then common source amplifier with diode connected load, and then common source amplifier with degeneration. Now we will see if this is the perfect way of biasing. How we were biasing the common source amplifier? VDD was there, then there was a small signal. This was the small signal input voltage, and then there was this DC bias. So VGG and VDD was responsible for the transistor to turn it on and to make it in saturation region. So VDD and VGG will make sure that your transistor is working in saturation region. But if you are using this biasing, this kind of biasing, what is the catch here? What is the issue? You are using two batteries, VDD and VGG. Here, for giving the DC bias, for giving the DC bias, you need to use two supplies, two battery or two supplies, and that are VDD and VGG. And this is not desirable. When I am designing a particular chip, when I am designing a chip, I will have only one supply, that is VDD. I will not have separately VGG. I can make VGG from VDD. How will I make VGG from VDD? By potential divider. That's it. So this is not desirable. Not desirable. Two supplies are not desirable. I will use only one supply. I will use only one supply. So how will I get VGG then? By potential divider. That is how I will get VGG. So this is the correct way of biasing. This is the first one. We will study more ways of biasing. So this is the first one. So this is the correct way of biasing. What I have done, I am using only one supply, that is VDD. Now this potential I can write down, right, and that will be VGG. Now instead of this V in, this is the small signal V in. Small signal V in. This is small signal input voltage. Here in this V in, you are not giving the VGG. This V in is simply Vm sin omega t. You are not giving VGG here. VGG you can get from VDD only. So here separately you can do DC and AC analysis. Let's do the DC analysis of the circuit. Let's do the DC analysis. So what will happen in case of DC analysis? In case of DC analysis, what happens to capacitor? Capacitors are open circuited. In case of DC analysis, capacitors are open circuited, right? That we have already seen. Capacitors are open circuited. Now what will be this V naught? Tell me. Will this V naught have DC output? Will this V naught have DC output? This is my question. No. Why so? Because there is this capacitor as well. This capacitor C. This is also known as coupling capacitor. This I can call CC1. This I can call CC2. This is also a coupling capacitor. What will happen? There will be some DC current through it. Your V naught here would be VDD minus ID into RD plus some DC output. Your V naught will be VDD minus ID into RD plus some AC output. Sorry, not DC output. DC output is, what is your DC output? That is VDD minus ID into RD. And this DC output will see some capacitor, CC2. It will see some capacitor. So it will not go up to V naught. This final V naught. So this final V naught is the small signal output only. So only small signal will be coming at the output. Are you getting this point? Only the small signal will be coming at the output. So whatever the DC was there, because of this DC2, the DC is not going towards the output. So here I will write small signal output. This shows our small signal output. This is small signal output. But for now we are doing the DC analysis. So this I am writing my DC output. This is my DC output. So what will be my DC output? What will be my VGS value? What will be my VGS value? VGS, that would be VDD into VDD into R2 upon R2 plus R1. That will be my VGS. Simply the potential divider, because the current here is 0 ampere. The current here is 0 ampere. The current is 0, so simply potential divider you can apply. R2 upon R2 plus R1 into VDD. This is your VGS. What will be your ID? This will be your ID. So your ID would be that constant value mu n cox w by 2l VGS minus VT whole square. VGS value you will be having, VT value you will be having, mu n cox w by 2l value you will be having. So you can calculate ID from that. And then what will be your output? Output will be VDD minus ID into RD. That's it. That will be your output. This will be your ID. So you have to set the value of R2, R1 and RD such that your VDS is greater than VGS minus VT. You have to set the value of R1, R2 and RD such that your VDS is greater than VGS minus VT. Also, you have to set the value of R2 and R1 such that your VGS is greater than VT. First point, that is set R1 and R2 such that VGS is greater than VT. Because what is your VGS? That is VDD into R2 by R2 plus R1. That should be greater than VT. We have to set the value of R2 and R1 such that your VGS is greater than VT. This is the first point. And the second point should be, what should be the second point here? On the next page only I will have to write it. Set R2, R1 and RD such that your VDS is greater than VGS minus VT, right? So that it is working in saturation region. What does it ensure? Ensuring saturation region. Well and good. Let's do the, why it is written DC analysis. Let's do the AC analysis. Okay, why did I leave so much of pages there then? Okay, DC analysis is done. We will do the AC analysis now. Small signal analysis or AC analysis. So we will do the AC analysis now. What will happen in the AC analysis? This VDD will be gone. This VDD will also be gone. This cap will be shorted. In case of AC and in case of DC analysis, the cap was open circuited. The cap was open circuited. In this case, this will be shorted. This is shorted now, and this cap will also be shorted. This will also be shorted now. Now what will happen? Oh, and this is not V in. This is your small signal V in. Small signal V in. Everything is small signal V in, and this is your small signal output. This is your small signal output. So what will happen? This V in will directly come here. In case of small signal analysis, there is no use of R1 and R2. R1 and R2 are connected only to make sure that your large signal VGS is greater than VT and your VDS is greater than VGS minus VT. Are you getting this point? I have biased my amplifier such that when I am doing the AC analysis, this Vin is completely coming to the amplifier. There is no use of this R1 and R2. Are you getting this point or not? So this Vin is completely coming to the amplifier. Between drain to source, there is R not connected. Between drain to source. So this is drain, source is grounded, so R not can also be grounded. So between drain to source, R not is connected. Drain to source, R not is connected. And since this is grounded, source is grounded, so I am making this as grounded as well. Now this is Vin. What is your VGS value now? Small signal VGS value. What is your small signal VGS value? That is equals to Vin. So what will be the current? Current will be GM Vin. That current will be flowing from what? RD parallel R naught. This Vin is coming. The current is GM Vin. This GM Vin current is flowing from RD parallel R naught because from V0 to ground you see RD. From V0 to ground you see R naught. So from V0 to ground you have RD parallel R naught. So did you understand this point or not? So basically what is the scene here? The current is, again and again I am not going to draw this, just once more I am drawing it. The current is GM Vin that is flowing through RD parallel R naught. So what will be the gain? The gain here would be minus GM RD parallel R naught. That's it. This is the voltage gain, small signal voltage gain. Did you understand this point? This is the small signal voltage gain. That is minus GM RD parallel R naught. Did your gain reduced? Did your gain reduce? No, the gain is the same. But using only one battery or one supply, you have made this amplifier. In previously, you need to use two supplies. But here, by using only one supply, you have made this amplifier. There is no change in the gain. What is the change in the input resistance now? If they are saying this is my input resistance, let's calculate small signal input resistance. Let's calculate small signal input resistance. Let's replace this with small signal input resistance. What will be the small signal input resistance? What will happen to this? This will be completely shorted. VDD will be gone because we are doing the small signal analysis, and this V0 will be here. Here you need to calculate the resistance. From this node to ground, what do you see? From this node, from Vin, this node is Vin only. From Vin to ground you see R1. From Vin to ground you see R2. Here what is the current? 0 ampere current. So if I am saying I am applying a Vin and getting I in out of it, so what will be my R in? That would be V in by I in. So let's calculate V in by I in. So here this potential will also be V in. So V in by R1 plus this current plus this current, V in by R2 is equals to I in, right? This current plus this current V in by R1 plus V in by R2 is equals to I in. This zero, there is 0 ampere current in the input side, 0 ampere current in the MOS. So you just applied nodal at V in. What did you do? You applied nodal analysis at V in. So V in by R1 plus V in by R2 is equals to I in. So what is your V in by I in? That would be R1 parallel R2. Your R in is R1 parallel R2. That's it. And you can directly see it as well. How you can directly see it? Because from this node to ground, R1 parallel R2 is there. So while doing the AC analysis, you can replace this resistance by R1 parallel with R2. Basically, what you can do, like this is your amplifier. this is the simplest and smallest final circuit. So this will be replaced with RD parallel R naught, right? RD parallel R naught, because from V naught to ground you see RD parallel R naught, and this will be replaced from V in to ground you see RD parallel, sorry, R1 parallel R2. So this will be replaced with R1 parallel R2, and this will be your V in. That's it, right? Okay. And what if they ask you output resistance? Tell me what will be the output resistance? What will be the output resistance? What will be the output resistance? This CC will be gone. If you are calculating the output resistance, this V in will also be gone. V in is gone. Now VDD is also gone. These VDD are also gone. This is 0, this and this is also gone. So basically I can reduce it to R2 parallel with R1. From this node to ground you are having R2 parallel with R1. This is 0, this node is also 0. This node is at also 0 volt. So this is also grounded. So VGS is gone. What is your VGS value here? Small signal VGS. That is 0 volt. And what you are calculating? Output resistance. You are calculating output resistance. Here you are having R naught. So this R naught I will be placing with R naught parallel with RD. Why? Because from this node to ground, from V naught to ground you can see RD, from V naught to ground you can see R naught. So collectively I can write R naught parallel with RD. This I can remove, and collectively I can write R naught parallel with RD. So here this is gone, so here there is 0 ampere current. There is this 0 ampere current. So from V naught to ground, what do you see? R naught parallel with RD. So what is your output resistance? R naught parallel with RD. That's it. This is your output resistance. Right, what we are doing, we are applying a voltage V naught and getting I naught current out of it. So what will be your V naught by R naught parallel with RD is equals to I naught. Why so? Because there is 0 ampere current. So that's it. So the complete I naught current is flowing through R naught parallel with RD. So what is your V naught by I naught? That is R naught parallel with RD only. That's it. So your output resistance is R naught parallel with RD. Right? And there is no use of writing current again. So let's forget about the current again. They will not ask you current gain. Input resistance, output resistance, and voltage gain. This is what they ask. Right? And also if they ask current gain, you can apply some equations and get to the final answer. Now, what we are going to do? Yeah, there will be one question. Why did you use this coupling capacitor? Why did I use this coupling capacitor? This is the question. Try telling the answer on your own. You have seen the DC analysis, you have seen the AC analysis. What is the use of this coupling capacitor? If this coupling capacitor was not there, what would have happened? I would have directly applied V in here. Now what is my V in? My V in is small signal input voltage only. This is not VGG plus V in. This is only VGG. What is my V in now? Only small signal input voltage. Previously what was my V in? Small signal voltage plus DC voltage as well. Now this V in is not having DC component. This is simply AC component. So what would have happened if this was not there? Even in the DC analysis, this V in would have come here, right? And that would turn off the transistor because that is very small. So when you are doing the large signal analysis, what is happening is that this V in is not coming. The small signal input is not even coming. So you can set your operating point. And while doing the AC analysis, it is directly coming. So you can get your final output. Are you getting this point or not? So the coupling capacitor, what does the coupling capacitor do? It prevents VGS to be equals to small signal V. If coupling capacitor is there, what will happen? Your VGS will be equals to, capital VGS will be equals to R2 upon R2 plus R1 into VDD. And if coupling capacitor was not there, only the short circuit path was there, then your VGS would have been small signal V in only. So that is the issue. So what is the use of this coupling capacitor? It is not letting V in come to directly MOSFET, right? So this we will write, use of coupling capacitor. अरे यार, so I will write it down. Yeah, so this is the reason why do we use coupling capacitor. So first is it helps in isolating the DC bias setting, helps in isolating the DC bias setting, and second one is, here what did I tell you, in the output you are having only the small signal output, that means you are having only the AC output. So let's assume if you are cascading mostly, what do you mean by cascading, that we will see. Okay, no worries, if you don't know what do you mean by cascading, we will see it in further lectures, but let's just write down the point here, that is, if you are cascading most stages, let's assume this particular amplifier, I am connecting this amplifier here, whatever the amplifier that I have connected here, the same amplifier I am connecting at the output. So what will happen? Only the AC part will be going towards the output. DC part will not go, because you don't want the DC, you only want the AC. So coupling capacitor helps in preventing the DC part to go to the next stage. It will block the DC part, only the AC part will go. And from where the DC part will come? Your DC part will come from the supply. So it helps in isolating the DC setting, DC supply setting. So this is what we have written, helps in isolating the DC bias setting. And if you are cascading two or more stages, then only AC signal from the first stage will pass to the second stage and DC will be blocked. So if you are cascading two or more stages, then only AC signal from the first stage will pass to the second stage, to the next stage, while DC is blocked. Are you getting this point? Only the AC will pass, and how the DC will come? DC will come from the supply that you are giving, VDD. That will be VDD into R2 by R1 plus R2. Well and good? Yeah. So this is the use of coupling capacitor. They can ask you in interviews that what is the use of coupling capacitor, or in simple MCQ as well. Yeah. So now what we will see? Yeah, there is one more condition, that is, if your small signal input source is having some resistance Rs. Here this was your small signal input, so it was not having any resistance, now what we are saying, this is your Vin, this complete is your Vin, this is your small signal input voltage, basically what is the scene now? The scene is something like this. This is R1, this is R2, this is RD, this is V0, this is VDD, this is VDD, this was the coupling capacitor. Till now everything is same. Here what did we do? We applied Vin. Now instead of this Vin, we are going to apply the source plus Rs resistance. So it is having some input resistance Rs. What changes it will bring? What changes it will bring in DC analysis? Will there be any change in DC analysis? No, because in DC analysis, this complete stage will be eradicated. This complete stage will not come, because capacitor will be open circuited, so this complete stage will not come. So there will be no change in the DC analysis, but there will be change in the AC analysis. What that change will be? Let's check that out. So let's do the small signal analysis. Let's do the small signal analysis. So in the small signal analysis, this will be shorted. This VDD is gone. This VDD will also be shorted. So from this node to ground, you can see R1. From this node to ground, you can see R2. So what you can do, you can replace this resistance as R2 parallel with R1. Well and good. This will also be shorted. So this will be your V0. Now can you write that this potential will be Vs and GM Vs current is flowing through it. Can you write this thing? No. What you can write? That this potential will be some V. This potential will be some V. We don't know what is V, and GMV current will be flowing here. So your V naught, this VDD is also grounded, sorry. And at V naught you are having R naught as well. R naught as well. So basically this writing like this is wrong. So GMV current will be flowing here. GMV current will not be flowing through RD. GMV current will be flowing through the MOS, and that current will go into RD parallel R naught, because from V naught to ground you see RD as well and R naught as well. So from V naught to ground you can replace it with RD parallel R naught. What will be your V naught? V naught will be GMV into RD parallel R naught. So your V naught will be minus GM RD parallel R naught into V. Now what will be your V? This is equation 1. What will be your V in terms of Vs? Tell me. This current is 0. This current is 0. So what will be the V? Simply the potential divider, right? So V will be R2 parallel R1 upon R2 parallel R1 plus RS into Vs, right? This will be your V. This was your V naught. This is equation 1, this is equation 2. Did you understand this or not? This is having RS, this is R2 parallel R1. Basically this is the same. R1, R2, V in. This potential. What is your V naught? R2 upon R2 plus R1 into V in, right? So this is what we are doing here. The same thing. The input current is 0, so you can simply say that the same current will be flowing here. Whatever the current is flowing through RS, the same current will be flowing through R2 parallel R1. So your V potential will be R2 parallel R1 upon R2 parallel R1 plus RS into Vs. So that will be your V potential, right? So what will be your V naught? V naught will be minus GM RD parallel R naught into R2 parallel R1 upon R2 parallel R1 plus RS into Vs, and if you are writing the gain, this Vs will come here. This is your small signal gain. So it is the same as the previous one. The difference is this factor. So your gain is reduced if your input is having some source resistance. If your input source is having some resistance with it, then your gain will be reduced, because the complete Vs is not coming at the gate. The complete Vs is not coming at the gate. This is the gate. So the complete Vs is not coming at the gate. What is coming at the gate? At the gate, R2 by R1 upon R2 by R1 plus RS is coming. At the gate, R2 by R1 upon R2 parallel R1 upon R2 parallel R1 plus RS into Vs is coming at the gate. Previously, what was coming at the gate? At the gate, complete input was coming. Previously, at the gate, complete input was coming. But now, complete input is not coming. What is coming at the input? This time, at the input, R2 by R2 parallel R1 upon R2 parallel R1 plus RS into Vs is coming. Now, that is amplified to output. Amplified by the factor of GM, and that is going to output. So GM into R0 parallel RD minus sign into R2 parallel R1 upon R2 parallel R1 plus RS. This is your small signal voltage gain. I hope you are feeling the chapter. These kind of expression seems very complex to a lot of people, but now it is not complex at all. You are simply doing the network analysis, nothing else. You are playing with the current. Just find the voltage, get the current, write the output. That's it. This is what you are doing. Well and good. So this was the voltage gain. This was the voltage gain we calculated. Can you tell me what will be the input resistance? Input resistance. So I guess we can copy this circuit only, or it has been copied only. So in the next slide we will write resistance is input resistance, output resistance, everything we will write. So tell me what will be the input resistance. This VDD will be shorted. So if this is shorted, R2 parallel with R1 will come. This VDD will also be shorted. So from V0 you will see RD parallel with, from V0 you will see RD parallel R0. This is your V0. Let's make it better. Let's make RS here. So if they are asking you what is the resistance seen from here, tell me what is your answer. What is your Rin? What is the resistance seen from here? RS plus R1 parallel with R2. Say yes or no. If they ask you what is the resistance seen from here, what is the resistance seen from here? That is R1 parallel with R2 only. This I can call Rin2. So no one will say that what is the input resistance of common source amplifier, nothing like that. They will make the circuit and they will make the arrow. They will make the arrow and they will ask you how much resistance do you see from here? How much resistance do you see from here? RS plus R1 parallel with R2, right? Because RS and R1 parallel R2 is having the same current. If I current is flowing here, if IS current is flowing here, the same IS current will be flowing here as well. Because the gate will not have any current. This will not have any current. This will have 0 ampere current. So the same current. Now what if they ask you the resistance from here? So RS is gone. Only R1 parallel with R2 you can see. Only R1 parallel R2 you will see. Right? So this was your input resistance. Input resistance. Now what about the output resistance? So while writing the output resistance, what you will do? You will short circuit the Vs. You will short circuit the Vs. Short circuiting the Vs. This RS will be shorted. From here, this R1 parallel with R2 will be shorted. This is your V0 and this is RD parallel R0. Look, these complete are shorted now, right? So R1 parallel with R2 parallel with RS. There is one single resistance. What is the current here? 0 ampere current. Is there any source here? Is there any source which can supply current? No, right? There is no source which can supply current. So this 0 ampere current will be flowing through RS as well and will be flowing through R1 parallel with R2 as well. So there is no current flowing through RS and R1 parallel R2. So whatever the ground is there, that will come here only. This will be 0 volt only. Are you getting this point or not? Or let's just forget it. Let's assume this potential is V. This potential is V. So V by RS, I am applying nodal here. V by RS plus V by R1 parallel with R2. Output current I am writing. Plus 0 is equals to 0. So what is the value of V you are getting? 0. Right? V by RS plus V by R1 parallel with R2 plus 0 ampere. All the outward current is equals to 0. So what is the value of V you are getting? 0. So basically, this node, this particular node is shorted only now. So again VGS is 0. So again there is 0 ampere current here. So if 0 ampere current is here, that means the resistance you see from here is RD parallel with R0 only. Did you understand this point or not? The gate becomes shorted. If the gate is shorted, source is already shorted. So the current here is 0 ampere. If the current is 0 ampere, that means MOSFET is acting as an open circuit. If MOSFET is acting as an open circuit, so basically from output you only see RD parallel with R node. That's it. Understood? Well and good? Okay. Let's move on to the next bias. But before moving on to the next bias, we have to study a theorem that is known as Miller's theorem. Very easy, very intuitive, and very interesting theorem it is. So let's forget about the statement, whatever that is written on the screen. Forget about this. First, we will understand what is the theorem, what does the theorem says, and then we will see the proof. So what does the theorem say? There is an impedance Z is connected. Now across the impedance, there are two nodes, V1 and V2. Now V1 and V2 are related by a factor of A. V2 is equals to A V1. Impedance Z is there. Impedance Z has two nodes, V1 and V2. V2 is equals to A V1. Now you can break this impedance Z into two parts. So what you will say, I am breaking the impedance Z into two parts. So what you will say, from V1 to ground, I see the impedance Z, that is Z upon 1 minus A. From V1 to ground, I see an impedance that is Z upon 1 minus A. Or what you will say, from V2 to ground, I see an impedance that is Z upon 1 minus 1 by A. So this is the Miller's theorem. You break down this impedance into two parts. Z was connected between V1 and V2. V2 was A into V1. So from V1 to ground you could see Z upon 1 minus A. From V2 to ground you could see Z upon 1 minus 1 by A. That's it. Well and good. Now let's prove this particular theorem. So what we are going to do, this is my V1, this is my V2, V2 is A V1. So from V1 to ground, I will see a resistance. I should say I will see a impedance. That value I don't know, I am calling this as Z1. So from V1 to ground, I see a impedance that is Z1. And from V1, I1 current is getting out. And from V2 to ground, I will see an impedance. That also I don't know. What is that impedance? I will call that as Z2. So my target is to find the value of Z1 and Z2. What is Z1? Z1 is V1 by I1. This is Z1. This is what I need to find. And what is Z2? Z2 is V2 by I2. So this is what I need to find, Z2. Right? So V1 minus V2 by Z is equals to I1. Are you agreeing to this point? See this circuit. V1 minus V2 by Z is equals to I1. Say yes or no. V1 minus V2 by Z is equals to I1. And what is V2? V2 is AV1. V2 is AV1. V2 is AV1. So what will be V1 by I1? That would be Z upon 1 minus A. And that is equals to Z1. Right? So basically your Z1 is coming out to be Z upon 1 minus A. What was Z1? Z1 was V1 by I1. Then what did I do? I have the circuit. I told that from V1 I1 current is flowing, from V2 I2 current is flowing. So basically V1 minus V2 by Z1 is equals to I1. So V1 minus V2 is AV1. So from there I am getting V1 by I1 is Z upon 1 minus A. So that is my Z1. What about Z2? What is Z2? Z2 is V2 by I2. So at V2 what I can apply, what I can write is that here what do you see? I1 is equals to minus I2, right? I1 is equals to minus I2. This is also true. So here only I can replace. If I replace I1 equals to minus I2, what I will get? V2 minus V1 by Z is equals to I2. Here I am replacing I1 equals to minus I2. So what I will get? V2 minus V1 by Z is equals to I2. Or from here also you can write V2 minus V1 by Z is equals to I2. That's it. What is V2? V2 is AV1. V2 is AV1. Okay, no. You need to find V2 by I2. So you will replace V1 by, what will be V1? V1 by V2 by A. V1 will be V2 by A by Z is equals to I2. So what will be your V2 by I2? V2 by I2 would be Z upon 1 minus 1 by A is equals to Z2. So this is the proof, right? Did you understand the proof? What was the proof? V1, V2 was V1 and V2 was linearly related by the factor of A. So from V1 to ground you could see a resistance that is Z upon 1 minus A. From V2 to ground you could see a resistance that is Z upon 1 minus 1 by A. So here, what did I do to prove the theorem? From V1 to ground I could see Z1 resistance, from V2 to ground I could see Z2 resistance. From V1 I1 current is flowing, from V2 I2 current is flowing. So I could simply apply a KCL KVL here. So V2 minus V1 by Z is equals to I1. So V2 is, what is V2? V2 is AV1. So from there, what is Z1? Z1 is Z1 upon 1 minus A. What about Z2? Z2 is V2 by I2. So V2 minus V1 by Z is equals to I2. What is V1? V1 is V2 by A. So from there I got to know Z upon 1 minus 1 by A. That is your Z2. Right? Now, these are the three questions that are in front of you. This is V1, this is V2. V2 is equals to AV1. That is given. V2 is equals to AV1. This is given. V2 is equals to AV1. This is given. So you need to write from V1 to ground. What will be the resistance you see? Tell me. From V1 to ground, what will be the resistance you see? That will be R upon 1 minus A. And from V2 to ground, what is the resistance you will see? From V2 to ground. From V2 to ground, you will see R upon 1 minus 1 by A. From V2 to ground, you will see R upon 1 minus 1 by A. I will write it in a better manner. R upon 1 minus 1 by A. From V1 to ground, R upon 1 minus A. From V2 to ground, R upon 1 minus 1 by A. What about inductor? From V1 to ground, what you will see? From V1 to ground, what you will see? L upon 1 minus A. From V2 to ground, what you will see? L upon 1 minus 1 by A. Now what about this one? From V1 to ground, what you will see? Tell me. Calculate it, then only tell the final answer. Don't be in a hurry. From V1 to ground, what you will see? So I will write down the option. C upon 1 minus A. 1 upon C into 1 minus A. C into 1 minus A. Three options are there. What will be your answer? C upon 1 minus A, 1 upon C into 1 minus A, C into 1 minus A. You are writing the capacitance, not the impedance. Note that you are writing the capacitance, not the impedance. The theorem we proved, this theorem we proved was for impedance. That your impedance will be Z upon 1 minus A. Right? Here, what was your impedance? What is the impedance provided by a resistance? That is R only. So that would be R upon 1 minus A. R upon 1 minus 1 by A. There is no issue with that. What is the impedance provided by the inductor? What is the impedance provided by a inductor? That is Ls, right? Or j omega L. You can write Ls as well, where S is j omega. So the impedance provided by a inductor is Ls, right? So what will be the impedance looking from V1 terminal? From V1 to ground, you would see Ls upon 1 minus A. So if that is the impedance, so what will be the inductance? Inductance will be this much, L into 1 minus A, right? That will be the inductance. Similarly, from V2, what you will see? From V2 to ground, you will see the impedance to be Ls upon 1 minus 1 by A. This is the impedance. If this is the impedance, then what will be the inductance? If I am saying my impedance is 5S, this is the impedance provided by an inductor. So what will be the inductance value? 5 Henry, right? Because the impedance provided by the inductor is Ls. So comparing L, that would be 5 Henry. Are you getting this point? What is the impedance provided by a capacitance? What is the impedance provided by a capacitance? That is 1 by Cs. 1 by Cs. So from V1 to ground, what you will see? 1 by Cs upon 1 minus A, or you can say 1 by C into 1 minus A into S. This is what you will see. From V1 to ground, you will see 1 upon C into 1 minus A into S. If I am saying I am having 1 by 5 as impedance, this is provided by a capacitor. The impedance provided by a capacitor is 1 by 5s. So what is the value of capacitance? 5. If the impedance provided by a capacitor is 1 by 7s, what is the value of capacitor? 7. If the impedance provided by a capacitor is 1 by C into 1 minus A, then what is the value of capacitance? C into 1 minus A. The impedance provided by the capacitance is 1 upon C into 1 minus A into S. Then what is the value of capacitance? The value of capacitance is C into 1 minus A. Are you getting this point or not? So the value of capacitance here would be C into 1 minus A. Did you understand this or not? So the correct answer will be this. For the inductor, L upon 1 minus A. L upon 1 minus 1 by A. For resistance, R upon 1 minus A, R upon 1 minus 1 by A. For the capacitance, for the capacitance, C into 1 minus A. That is the capacitance. This we are C into 1 minus A. This is the capacitance. What will be the impedance provided? That would be 1 upon Cs into 1 minus A. That would be the impedance. Are you getting this point or not? Say yes or no. Right? So this is the impedance provided. If you know the impedance provided, then you can write down the value of capacitance. Right? This is simple network analysis only, but still I know a lot of guys are not comfortable in network analysis as well. Yeah. So this we have explained. And tell me what will be the value V2 will see. How much capacitance V2 will see. This you should be able to write down. First treat it as 1 by Cs. If 1 by Cs was there, what was the impedance it would see? 1 by Cs upon 1 minus 1 by A. So 1 by C into 1 minus 1 by A into S. If the impedance provided by the capacitance is 1 upon C into 1 minus 1 by A into S, then what is the value of capacitance? This is the value of capacitance. So the value of capacitance is C into 1 minus 1 by A. So C into 1 minus 1 by A. This would be C into 1 minus 1 by A. So from V1 to ground, you could see C into 1 minus A. From V2 to ground, this would be C into 1 minus 1 by A. And this is very, very important. It will be highly used when we study the frequency response. When we study the frequency response, this is very important, and this is also important. In analog circuits, we don't use inductor much. Inductor is used in high frequency circuits. So one or two example we may see for inductor as well, but mainly capacitance and resistor will be used. So this is the theorem. This is Miller's theorem. We have seen three questions here. V1, V2, V1, V2 is connected. V2 is AV1. So what will be the resistance here? R upon 1 minus 1 by R upon 1 minus A, and here R upon 1 minus 1 by A. Similarly, C into 1 minus A and C into 1 minus 1 by A. Well and good. Let's move on to a question. What is this? Common source amplifier with degeneration, and R0 is considered. Here, instead of writing this, what I would have written, I should have written that your lambda is not equals to 0. That means your R0 is finite. R0 is not infinity. So here your R0 will be considered. Now you will say, sir, you told us that you should not remember that formula because no one will ask you this question. That common source amplifier, they can ask you the gain of common source amplifier. What did I tell you? I told you that they can ask you the gain of common source amplifier with degeneration, but they will say that R0 is infinity. This is what they will say. Right? But here they are not saying R0 is infinity. Here they are saying R0 is finite. So how will you calculate the gain now? So that we will apply the formula and then we will calculate. But that will take a lot of time. So what is the shortcut? What is the catch here? How will you do it smartly? So let's check that out. What did I tell you? If there is a resistance and the resistance will be having two nodes. This resistance is having one node is V node, the other node I can call Vx. If there is a linear relation between Vx and V node, then you can apply Miller's theorem. So is there any relation? What you can see here is that here Vx by R naught is equals to minus V naught by 2 R naught. Say yes or no. This current is equals to negative of this current. Vx by R naught is equals to minus V naught by 2 R naught. Well and good. So what is your V naught by Vx? That is minus 2. So basically your V naught is minus 2 Vx. V naught is minus 2 Vx. So this V naught I can write down is minus 2 Vx. So now what you can say? From Vx to ground, what was the scene? Impedance Z was there. This was V1. This was V2. V2 was A V1. So from V1 to ground, what I could see? From V1 to ground, what I could see? Z upon 1 minus 1 by A. The one which is alone. What is alone? Who is alone here? Okay, wait a second. Did I do any calculation mistake here? Did I do any calculation mistake? Vx by 2R, Vx by R naught. Yeah. So V1 is this side. V1 is this side. V2 is depending on V1 by minus 2. Right? So from V1 to ground, what do you see? Z upon 1 minus A. So from Vx to ground, what you will see? R naught upon 1 minus A, and A is 2. So R naught upon 1 plus 2. R naught by 3 you will see. Are you agreeing to this point or not? So did you understand this? This is Vx, this is minus 2 Vx. This is Vx, this is minus 2 Vx. The one which is alone, that we will say, that guy will say that from Vx to ground I will see R naught upon 1 minus A, and A is minus 2. So R naught by 3. So the one which is alone, that will have 1 minus A, and the one which is not alone, this guy is not alone, this is having minus 2 with it. So what it will say? From V0 to ground I will have R naught upon 1 minus 1 by A. That means R naught upon 1 minus 1 by 2. So R naught upon 3 by 2. That means 2 R naught by 3. So we will write it down. So what it will say? This was the thing that we have already studied. Let's close it in a box. So yeah. So what Vx will say? That from Vx to ground I will see, from Vx to ground I will see R naught upon 1 minus A, that is 2. So that would be R naught by 3. And what V naught will say? V naught will say that from V0 to ground, I will see R naught upon 1 minus 1 by A, that is 1 by 2. So it will be 2 R naught by 3. From V0 to ground I will see R naught upon 1 minus 1 by A. 1 minus 1 by A. A is minus 2. Here your A is minus 2. A is minus 2. A is minus 2. A you are getting is minus 2. So this will be 2 R naught by 3. This is R naught by 3. So how your circuit is reduced now? From V0 to ground you are having R naught by 3, and here, sorry, from V0 to ground you are having 2 R naught by 3, and from Vx to ground you are having R naught by 3. So this R naught parallel with R naught by 3. Are you getting this point? These will come in parallel. So let's add a page. This was very interesting question. These kind of questions are not asked in GATE yet, but certainly they will be asked, and I am telling you, forget about the student. Even the teachers will not be able to answer. Now, please don't think I am arrogant or anything, but I have seen the content by the educators, how they teach in GATE field. So yeah, so there are many loopholes. So these kind of loopholes are there which needs to be filled, and we will fill it. So here we are having V. This is your V naught. This was your Vx, and in between you had R naught. So this was your R naught. This was your 2 R naught. So what did you concluded? That from V0 to ground you will see R naught by 1 plus 1 by 2. So from V0 to ground you will see 2 R naught by 3, and this 2 R naught is already there. So 2 R naught parallel with 2 R naught by 3. If you calculate it, it will be, as far as I remember, it will be R naught by 2. You can calculate, right? 2 R naught parallel with 2 R naught by 3. So 8 R naught by 3. So this will be 4 R naught by 2. Yeah. So parallel combination will be R naught by 2. And what about this? R naught parallel with 2 R naught. So no, sorry. R naught parallel with R naught by 3. So from V naught to from Vx to ground. From Vx to ground we are saying R naught by 3. So what is that combination? R naught into R naught by 3 plus 4 R naught by 3. R naught by 4. This will be R naught by 4. R naught by 4. This is R naught by 2. So what is the value of V naught by V in now? Our target was to find the V naught by V in. Our target was to find the V naught by V in, right? But if we had found V naught by V in by applying equations, it would be a bit difficult. So better we solve it like this. So what will be our V naught by V in now? We already remember what is V naught by V in. That is minus Gm Rd. What is our Rd now? Rd is R naught by 2 upon 1 plus Gm Rs. What is our Rs now? R naught by 4. That would be minus Gm R naught by 2 plus divided by 4 plus Gm R naught by 4. That would be minus 2 Gm R naught upon 4 plus Gm R naught. This will be your V naught by V in. Well and good. Did you understand this problem or not? What did I do here? I could have simply calculated with the other method as well by writing down the equation, but I needed to apply Miller's theorem. So I applied the Miller's theorem. Vx and V naught, I could find that they are having a linear relation. That is, V naught is equals to minus 2 Vx. So from V naught to ground, I will see R naught upon 1 plus 1 by 2. So 2 R naught by 3, and from Vx to ground, I will see R naught by 3. Now circuit is reduced like this. Now for this configuration, I remember the final answer. That is minus Gm Rd upon 1 plus Gm Rs. Minus Gm into Rd. This is our Rd. So Rd is R naught by 2 upon 1 plus Gm Rs. This is our Rs. That will be 1 plus R naught by 4. And if you don't remember, from here also you can calculate the final answer. But this is the common formula which everyone remembers. So even if you don't remember, from here you can calculate. And if you remember, you can directly apply the formula minus Gm Rd upon 1 plus Gm Rs minus Gm R naught by 2 upon 1 plus Gm R naught by 4. 4 1 4 is there. 2 will go upward, minus 2 Gm R naught upon 4 plus Gm R naught. So this is how I calculated the final answer. There are other ways as well. You can find, simply write down the equation and you will get to the final answer. I guess that will also not be very complex, right? Because if you just apply the equation, that will also not be very complex. You will also get to the final answer very easily. Okay, so you can apply the equations as well, and or by using this thing, by applying the Miller's theorem, you can also calculate. Well and good. Let's see the other way of biasing. So why did we study Miller's theorem? Out of nowhere, suddenly I taught you Miller's theorem. Why? Because we are going to use it. So first we studied about this biasing, that potential divider. Here we are doing the potential divider. So I will call it potential divider biasing. There is no specific name. So let's just call it potential divider. So first we studied about this biasing. This was the first way. I hope you have understood it. You could write down the VGS value. You could write down the V naught value. Then you could do the small signal analysis. When you did the small signal analysis, you could find out the gain. Then you could find out the input resistance. Then you took the condition that your input is having the RS resistance. Then you find out the gain again, and you find out the input resistance and output resistance, right? Then suddenly I taught you Miller's theorem. Why so? Because now I am going to teach you another way of biasing, that is self-bias. So what different we are going to do here? Self-bias circuit. This is the self-bias circuit. So what is happening here? Yeah. So let's do the DC analysis. In DC analysis, this will be gone. What is this? This is small signal input voltage. Small signal input voltage. This is small signal input voltage. So what will happen? In DC analysis, what will happen? This will simply be replaced with RD. This is grounded, and this is RS, and this is your V naught. This will be VDD. right? Tell me one thing, is there any current in this resistance RS? Is there any current? 0 ampere current is there. You are doing the DC analysis. Why 0 ampere current? Because this will be 0 ampere current. If this is 0 ampere current, then the same current is flowing in this loop. So there will be no current in the RS, right? There will be no current in the RS. So your VGS, capital VGS is equals to V naught only. And what is your VDS? VDS is also V naught. There is no current, so VDS is also V naught, VGS is also V naught. What is your V overdrive? V overdrive is VGS minus VT, that is V naught minus VT. So here what you can see, your VDS is greater than V overdrive. That means it is always in saturation. So you don't have to worry about this transistor. Here, this transistor will always be in saturation. The only concern is what will happen? Here ID current will be flowing. Now there is zero current, so the same ID current will be flowing here. So the only concern is that VDD minus ID into RD should be greater than 0. Because to turn on the transistor, your VDS should be greater than 0, right? Your VDS should be greater than 0. So only concern is VDD minus ID RD should be greater than 0 and should be greater than VT as well. Why so? Because this is equals to VGS as well. V naught is equals to VGS. So VGS should be greater than VT. And what is VGS? VGS is V naught. And what is V naught? V naught is VDD minus ID into RD. So your only concern is make sure that VDD minus ID into RD is greater than VT. That's it. Ensuring what this will ensure? Ensuring that MOS is on. And if MOS is on, it will certainly go into saturation region. There is no chance it will go into linear region. There is no chance that this configuration can go into linear region. This will certainly be in saturation region. Why so? Because your VGS is V naught, VDS is V naught, and V overdrive is V naught minus VT. So that means VDS will always be greater than V overdrive. So it will always be in saturation. Let's assume my V naught is 3 volt, my VT is 1 volt. So what will be my V overdrive? 2 volt. What will be my VDS? That will be 3 volt. So 3 volt will always be greater than 2. So always VDS will be greater than V overdrive. So always it will be in saturation, and you have to make sure that your VDD minus ID into RD, that means your VDS or VGS should be greater than VT. That will ensure that your transistor is on, your MOSFET is on. So this is what you need to ensure. So this is the advantage here, right? Now let's do the AC analysis of this configuration. We are doing the small signal analysis. Now there is a catch in Miller's theorem, and that you will realize here. So this is your Vs, this is your V0. Now what people generally do, those who have already studied, they might have done this thing as well. What they will do, that here we are having RS resistance, this is the RS resistance, this is Vs, one node of RS is connected to Vs, and the other node of R, this should not be RS, this should be RF. I should write it as RF, R feedback. Okay, I'm really sorry, I'm writing RS, it should be R feedback, RF, R feedback. This should be R feedback. So now what will some people say? Some people will say that, sir, one node of RF is connected to Vs and the other node of RS is connected to V0, right? So what they will say, sir, V0 is minus Gm into RD into Vs, because this is common source amplifier. So V0 is minus Gm into RD into Vs. So what I can do, I can apply Miller's theorem, and at the input side from the Vs, what I can write, Rf upon 1 minus A, that means Rf upon 1 plus GMRD, and the output side, what I can write from V0 side, at the node of V0, what I can write, Rf upon 1 plus 1 by GMRD. And now this particular thing is completely wrong. This is completely wrong. Why is it so? Why is it so? What is the catch here? What is what we are doing wrong here. Why it is wrong? What did I tell you? That Vs and V naught should be linearly related. So it is related by the factor of minus GMRD. Is that correct? When your RF is connected, then will your V naught will be GMRD Vs? It will not be. Why so? Let's check that out. This is Vs, your Vjs is Vs, so what will be the current? GMVs. Now will that current flow from RD? Will that current completely flow from RD? Say yes or no. No, the current will not completely flow from RD. That current can go into RF as well. Now you will not say, sir, this current is zero. So how RF will have current? Kyun? The source can drive some current. The source can also drive some current. So the RF current will go into the source completely. So RF can also have some current. In case of DC analysis, RF was not having any current because there was no supply here. So the current has to flow like this. But here we are having the supply. Here we are having the Vs. So even if the current is 0 ampere, even if the input current is 0 ampere, that doesn't mean that RF cannot have some current. Whatever the current RF is having, that will go into the supply, or supply can drive some current. So here we are having Vs, here we are having a node. This will be a battery. So from battery, current can go out, current can come in. So you can't say that RF cannot have some current. RF will have some current. So if RF is having some current, that means the complete GMVS is not going into RD. So V naught is not minus GMRD into Vs. V naught is something different. Are you getting this point? So that we have to find what is V naught. Say yes or no. Understood? So that is wrong here. A lot of time people write it down this way, that V naught is minus GM into RD into Vs, then we can apply this thing. When this will be applicable? When this thing will be applicable? Tell me. When RF is too large. So whenever you are applying Miller's theorem, you need to make sure that your RF, whatever that you have connected, this impedance is very large. If this impedance is very large, then what will happen? The GMVS current will completely flow from RD. Because if RF is very large, it will not drive any current. The complete current will flow from RD. So this is the catch when we are applying the Miller's theorem, and every time we ignore it. So in the examination as well, it will be written that your RF is very large. If RF is very large, that means it will not drive any current. That means the complete GMVS will be flowing through RD. So your V naught will be minus GM into RD into Vs. Now you can apply the Miller's theorem. So in the examination, it will be written. Now let's assume in case of RF, if there was capacitance connected. In case of RF, there was capacitance connected. Then what would have been written in the examination? That CF is very large or very low? Very low, right? In the examination, it would have been written that CF is very low. If CF is very low, that means impedance provided by this will be very large. If CF is very low, what is the impedance provided by the capacitor? That is 1 by CFS. So impedance provided by this will be very large. So the CF will not drive any current. Otherwise, it will drive any current. Well and good. Understood? So here also, this RF will drive some current. So it's not that you can apply Miller's theorem directly. You can apply Miller's theorem, but the value of V naught will be different. Value of V naught will not be this. This is wrong here, right? So the wrong thing is this. So let's write down the correct answer. Also, there will be R naught as well. So there will be R naught as well. RD parallel R naught you can write. So R naught also we will consider. So let's do the correct analysis. What will be the correct analysis? Let's do that. We are doing the AC analysis, so this VDD will already be gone. So this was the MOS. Here you are having the RF. This is V naught. This is ground. So from V naught to ground you are having RD. And also from V naught to ground you are having R naught as well. Because R naught is connected between drain to source. So RD parallel with R naught. This is your Vs. And the current flowing here would be GM into Vs. that current will go from RF as well and from RD parallel R0 as well. The current will go from RF also from RD parallel R0. So what you can do, you can apply nodal analysis and then you can find out the final answer. What I am saying, you can apply nodal analysis, nodal at V0, nodal at V0. So what that would give you, V0 into RD, V0 plus RD by R0, sorry, V0 by RD parallel R0 plus GMVS, this current plus this current plus this current now, plus V0 minus Vs by Rf is equals to 0. From here you can find out the value of V0 by Vs, right? You can find it out on your own. Or do you want me to write it down? Okay, I will write it down. Okay, so let's write it down. This was the equation. I hope nothing is wrong here. V0 by RD upon R0, GMVS and V0 minus Vs by Rf. Okay, all the current I have written. From V0 node, this current plus this current plus this current. Nothing else is there. So what I can see here is that V0 by RD parallel R0 plus V0 by Rf is there, is equals to, no, plus GMVS is equals to Vs by Rf plus GMVS is equals to Vs by Rf, Vs by Rf minus GMVS. All correct? All correct. Yeah. So this would be V0 by Rf parallel with RD parallel with R0 would be equals to Vs by minus 1 by Gm parallel with Rf. Is that so? Minus 1 by Gm parallel with Rf. So what is your V0 by Vs now? That is Rf parallel with RD parallel with R0 minus 1 by Gm parallel with Rf. Right? This is V0 by Vs. Is that correct? Let me check the calculation. Yeah, so that is correct. That will be the gain. There is one more way of writing the gain. We will see method 2 of writing the gain. Method 2. Okay, one more way is there. That is method 2. What is the other way? So the MOS circuit is given. This is grounded. From V0, what you can see, RD parallel R0. Here there was Vs, and between this was the scene, right? RF, right? This was the scene. So this Vs is applied to MOS as well. This Vs is applied to MOS as well and also to RF as well. So I can write it down in this manner. Are you satisfied with this? I can write it down in this manner. Vs is applied to both MOS and MOS as well and RF as well, right? Vs is applied to MOS as well and RF as well. And from V0 to ground you see RD parallel R0. So now I can apply superposition. Applying superposition. So first I will consider only this one. First I will consider only Vs, this one. So what will be my V0? This will be shorted. So from V0 to ground, RD parallel with R0 parallel with RF will come. So what will be my V0? That would be minus Gm RD parallel with R0 parallel with RF into Vs plus. Now what I will do? I will consider only this Vs. Sorry, I will consider only this Vs and this will be grounded. Now if this is grounded, then what will happen? There is no current in this MOS. If Vs is grounded, there is no current in this MOS. Say yes or no. There is no current in this MOS. So this will simply be open circuited. If this is open circuited, then what will be the scene? If you are not able to understand, I will explain it once again. No worries. But till now, try to understand it. So what will be the condition? This will be the condition, right? Vs, Rf, V0, Rd parallel R0, because there is no current in this MOS. MOS is open circuited. Why so? Because Vs is grounded. VGS is 0. So MOS is open circuited. So what will be your V0 now? V0 will be Rd parallel R0 upon Rf plus Rd parallel R0 into Vs. So what will be your V0 by Vs? That you can write down, minus Gm Rd parallel R0 parallel Rf plus Rd parallel R0 upon Rf plus Rd parallel R0. So that will be the gain. So in the examination, they can give you any expression. They can give you this expression as well. Like they will give you the configuration. They will ask you what is the gain. So in 4 options, you can have this expression as well, and you can have this expression as well. So you should be comfortable with both of the analysis. That what will be the gain. So this can also be the gain, and this can also be the gain, right? If you solve this and solve this, you will get the same answer. You can try solving it down. You will get the same answer. Okay, yeah. So what did we do here? What was the circuit? Let's revise it once again. So this was the circuit. Vs was applied to both MOS and RF. So what did we do? We applied superposition. First we consider only this Vs. We did not consider this Vs. So what will happen? This will be grounded. So RF parallel with Rd parallel with R0 will be there. RF parallel with Rd parallel with R0. So what will be your gain? This will become a simple common source amplifier. So what is the gain for common source amplifier? The current will be GMVS here. The current will be GMVS. The GMVS current will be flowing through the resistance Rd parallel with R0 parallel with Rf. So the gain would be minus Gm into Rd parallel with R0 parallel with Rf. That's it. Then we consider only this Vs. Only this Vs. Now this Vs will be shorted. Now if this Vs is shorted, that means the current is gone. The MOSFET current is gone. So only the potential divider seen will be there. So Rd parallel with R0 upon Rf plus Rd parallel with R0 into Vs. That will be your V0. So from V0 by Vs, you got to this answer. Well and good. Okay. Yeah. Now this is your gain A. This is your gain A. So if you were saying that this was my Vs, what you were saying that this was my Vs, and from Vs the RF was connected, and this was my V0. So your V0 was A Vs, where your A was what? This expression. This was your A. Are you getting this point? So your A was, I have to write it down again. Okay. I have to write it down, so I will write it down. Minus Gm Rd parallel R0 parallel Rf plus Rd parallel R0 upon Rf plus Rd parallel R0. Right? This is again A. Now you can say that, and now you can apply the superposition theorem. Now you can say that from Vs to ground, I will see, from Vs to ground, I will see Rs upon 1 minus A being this value, and from V0 to ground, I will see Rs upon 1 minus 1 by A, and A being this value. Say yes or no. Understood? Understood this analysis? So why did first I taught you the Miller's theorem, then I taught you the application of Miller's theorem, then I taught you where it cannot be applied. In the self-biased circuit, it cannot be directly applied, that you cannot directly say that my gain would be minus GMRD. No. My gain would be this much. So always, what is the main point that you understood here? That you always have to take in consideration this resistance RF. here in the previous notes here, that considering R, your V2 was AV1. Here considering L, your V2 was AV1. Here considering C, your V2 was AV2. Are you getting this point? Now in this one, considering R naught, even if this R naught is there, still your V naught is minus 2Vx. Are you getting this point? This R naught was there, still your V naught was minus 2Vx. If this R naught was not there, if this R naught was something else, if this R naught was some 6 R naught, then what would be your V naught? That will still be your minus 2Vx. Then you can again apply the Miller's theorem here. So considering R naught, we calculated V naught. Are you getting this point? Considering R naught, we calculated this V naught. What did we do? We applied this current is equals to minus this current. There is no role of R naught here. Are you getting this point? No matter whatever you put in this place, even if you put inductor, even if you put capacitor, even if you put any circuitry, even if you put diode, V naught will always be equals to minus 2Vx. Here also, by making sure that even if the resistance R is connected, your V2 will always be equals to AV1. Here also your V2 is equals to AV1. Here also V2 is equals to AV1, irrespective of capacitance, inductance or resistance. Here, but here, if we connected RF, the gain changed. If RF was not there, the gain would have been minus GM into RD. But if RF is connected, then the gain has changed. The gain has changed to, previously the gain was minus GMRD, now the gain has become this much. So the gain has changed. So if the gain is changed, then this value of resistance will also change. This is not RS, this is RF. So this was the main thing that we always forget, that we find the gain without considering the feedback resistance. What they do is that they forget this resistance, and they write down the gain. They write down the gain is minus GMRD. No, you have to consider this resistance. Considering this resistance, whatever the gain is, considering RF, what the gain you get, right? That will be your A. Your A will not be without RF. You have to consider RF. That is the catch. Okay. Now they can ask you more thing in the self-bias circuit. In the same circuit, they can ask you input resistance. So tell me what will be your answer for input resistance. So in the same circuit, they can ask you input resistance. Yeah. Small signal analysis we are doing. Input resistance means resistance from this side. R in. Tell me what you will do here. What you can do, from Vs to ground, you can replace this RF. That will be replaced by RF upon 1 minus A. And from V0 to ground, it will be replaced by, RF upon 1 minus 1 by A. Right? And this RF will be gone. So tell me what is the input resistance now? There is no current here. There is 0 ampere current. So what is the input resistance? Rin is simply RF upon 1 minus A. Well and good. And tell me what will be the output resistance? Input resistance slash output resistance. Tell me what will be the output resistance? R out. So for writing R out, what you will do? You will short circuit this. If Vs is shorted, that means there is 0 current in this one. So from V0 to ground, what do you see? RD you see parallel with this resistance. Also R0 is there. So RD parallel R0 parallel this resistance RF upon 1 minus. So this is the output resistance. This is the R0 you see from here, right? What is the R0 you see? RD parallel with R0, parallel with RF upon 1 minus 1 by A. Vs is shorted. If Vs is shorted, that means there is 0 current in the MOS. So MOS is simply open circuited. So RD parallel with R0, parallel with RF upon 1 minus 1 by A. 1 minus 1 by A. So this is the output resistance you see, and this is the input resistance. And what is the value of A? value of A is minus Gm Rd parallel with Rf parallel with R0 plus Rd parallel R0 upon Rd parallel R0 plus Rf. This is the value of A here. So you don't need to mug it up. All these things are for analysis purpose. It's not that I am asking you to remember all these things, but you should have the clear idea of the analysis, how we do the analysis, right? RF is there, V0 is V0 is related to Vs by a factor of A. What is the factor of A? This is the factor of A. What is R in? What is R0? So everything you are comfortable now. So why did we pick this self-biased circuit? First we did the DC analysis. DC analysis was very simple. You have to make sure that VDD minus ID into RD is greater than VT, ensuring MOS is on. Then we saw the AC analysis. Here what did we show? What is the wrong thing that people do? That is they write V0 equals to minus Gm into RD into Vs. They forget that there is RF connected. If RF is connected, the gain will be different. The gain will not be minus Gm into RD into Vs. So the gain will be different. So applying this thing is wrong. This you can apply only when correct only when RF is very high. RF is very high. If RF is very high, that means your V0 will be minus Gm into RD. V0 will be minus Gm into RD, so you can write down this expression then. So it is not usually correct. So for usually correction, you have to find out the value of V0 considering RF. So value of V0 considering RF you got is this much. Or you applied second method, then you got this much by applying the superposition. Then you got to know that this is Vs, this is V0. So they are linearly connected like this. So Vs to ground Rf upon 1 minus A, from V0 to ground Rf upon 1 minus 1 by A. So this is how you can replace. So you replaced your circuit something like this. So Rd was there, R0 was also there. From Vs to ground you replaced it Rf upon 1 minus A. From V0 to ground you replaced it Rf upon 1 minus 1 by A. So what is the output resistance? Output resistance is Rd parallel with R0 parallel with Rf upon 1 minus 1 by A. And what is the input resistance? That is Rf upon 1 minus A. And this is the gain. That's it. Are you able to understand? Now we are done with the common source amplifier. After this we will see an assignment. There we will cover up a lot of circuits. In the assignment we will cover up a lot of circuit. We will see every kind of biasing of common source amplifier. With that we will be done with the common source amplifier. So in the next lecture we will see an assignment, and that will help you a lot in understanding the problems. Okay, thank you.